All right, let's jump right in. We rely on logic for, well, pretty much everything, right? From the code running on your phone to big philosophical debates. But have you ever stopped and wondered, how do we know our systems of logic are actually correct? Today, we're going to explore how we can automate the very process of checking the rules of reason itself.
So this is really the fundamental question, the one that everything else hinges on. A proof system is basically the rulebook we use to build arguments that we know are valid. But what if that rulebook has a typo? What if one of the rules is just a little bit off? Everything we build with it could come crashing down. So how in the world do you check the rulebook itself?
The stakes here are just incredibly high. And this is a perfect analogy. Before you even think about pouring a concrete for a skyscraper, you have to be 100% sure the blueprints are perfect. You need to know that the laws of physics are applied correctly, that every calculation is sound, because one tiny mistake at that foundational level and the whole structure is at risk. Logic is exactly the same.
And that brings us to what's really been a grand challenge for logicians for decades. Making absolutely certain those foundational blueprints for reason are completely flawless.
Now, the technical name for these blueprints, these rulebooks, is sequence systems. They are the super formal, really structured guides that spell out precisely how you can take statements and combine them, step by step, to build a proof that you know holds up.
To check those blueprints, logicians have to run a series of critical safety checks. You can think of these as stress tests for the logic itself. They make sure the whole system is consistent, that it's efficient, and that it doesn't have any hidden, fatal flaws. Take cut admissibility, for example. That one is absolutely vital. It basically guarantees that we can use logical shortcuts without accidentally proving something that isn't true. Each one of these is like a critical guardrail for our reasoning.
And here's the really big problem. For the longest time, the only way to do these crucial checks was for a logician to literally sit down with a pencil and paper and just grind through them, by hand. Can you imagine trying to check every single beam and rivet in a skyscraper's blueprint manually?
This quote from the source material just nails the issue perfectly. That phrase, combinatorial nature, means that you have this massive, sprawling number of ways the rules can interact with each other. It gets complicated fast. So it's not just tedious work, it's a minefield for human error. One little mistake could slip by and completely undermine an entire logical framework.
So if doing it all by hand is so risky and just impossible to scale, what's the alternative? Well, this is where a really powerful approach comes into play. Enter rewriting logic.
This comparison really tells the whole story, doesn't it? Rewriting logic just completely transforms the game. It takes the process from this task of human endurance and turns it into a matter of computational precision. What used to be tedious is now algorithmic. What was error-prone is now automated and super reliable. It's a total paradigm shift.
So, what's the secret? The crucial insight, the big conceptual leap, is this. Instead of seeing logic as just a static book of rules that you read, rewriting logic treats it like a dynamic system of transformations, basically a computation. It turns the rules of logic into a program that a computer can actually run and analyze.
Okay, so that's the big idea. But let's see how this actually becomes a practical tool. How does this framework actually work in the real world?
Well, it boils down to this really neat three-step process called the L framework. First, you specify the rules of your logic in a formal language the machine can understand. Next, you mechanize it. You basically let the computer's powerful search algorithms loose on the problem. And then third, the framework just automatically verifies whether those critical safety checks like cut admissibility actually hold true.
And this isn't just some abstract theory. This whole automated process is built into real-world software tools. Maude is a great example. It's a system where you can literally plug in your logical rules and let the machine do all that heavy lifting of verification for you. And the results? They're seriously impressive. This framework has already been used to successfully verify the structural integrity of more than 10 different major logical systems. We're talking everything from the classic logic we all know to some pretty exotic ones. This isn't some niche solution. It's a robust, proven technique, and it's changing the field.
The ripple effects from this are just huge. I mean, we are witnessing nothing less than a revolution in how we establish logical certainty itself. And just look at the range here. It's been applied to classical logic, the kind you learn about in school, but it also works on more complex systems like linear logic, which reasons about resources, and modal logics, which deal with ideas like necessity and possibility. The versatility is just incredible.
So,
Why does all this matter? Well, because by automating these fundamental checks, we're building what the source material calls scaffolding. We're creating a reliable, solid base. This frees up human logicians to go after the really big questions, like proving the overall consistency of an entire system, because they can be confident that the foundation they're building on is rock solid.
And that leaves us with a pretty fascinating thought to chew on. For centuries, logic was the tool we used to verify everything else. But now we have tools to automatically verify logic. So the question is, with the very blueprints of reason now machine-checkable, what incredible new structures of thought will we be able to build next? What's the next frontier?